we're assuming that this satellite needs to stay geosynchronous, so it's going to stay above the Earth, so it has to rotate with the Earth. So then, and the height of the satellite. Okay, the height of the satellite is r, so its distance between the satellite and the Earth is r. Well, we know that the sum of the forces on that satellite are equal to mv squared over r. And the thing keeping the satellite in orbit is the universal law of gravitation, which says big G, m1, mass of the Earth, is mass of the satellite, over r squared is equal to m, mass of v squared over r. This r cancels with that ms cancels with this, and we get v, the velocity of the satellite around the Earth, is big G, me over little r. So that's the velocity now at orbit r. And we can see that if you put, so then I guess we can say what happens if you double, so this is v0. So what is v final if you double the radius? So it's big G me over 2r, right? We can factor that out and say that is equal to 1, like the square root of 1/2 times the square root of big G me over r. And then, of course, square root of 1 is 1, so it's square root of 1 over square root of 2. And then you have to multiply by square root of 2 over square root of 2, so you get this is equal to square root of 2 over 2 times big G me over r. And that's Vf. But do you see that this big G me over r, that is V0. So that means it's square root of 2 over 2 times V0. So how much does the time go up? It's the original time times square root of 2 over 2. So it's that multiplying factor. Now, please notice the mass of the satellite canceled. So this one is just the same. All right, and then we see the mass of Mars is 6.58 times 10 to the 23. So 6.58 times 10 to the 23 kilograms. So all we have to do is just look at this. All right. Oh yeah. Of course, on the side we should kind of say the time it takes to orbit is equal the distance divided by the velocity. So it's 2 pi r over v. Right. That's going to be the time that it takes. I don't know if that's totally necessary. Yeah, whatever. I mean, it's just going to be times the original, so it's not a big deal. So if we look at this and say, all right, the mass of the Earth is, I think, 5.96 times 10 to the 24th. So I would say that mass of the Earth is about, 15 times? Yeah, about, let me see. 59.6 divided by 6.58. No, not 15, it's 9. It's 9 times. So the mass of the Earth is equal to 9 mass of Mars. So that means the mass of Mars is equal to mass of the Earth over 9. So, if you want me to drag this up and then go back to this, we're going to get, remember our velocity around the Earth was square root of big G me over r. So our velocity around Mars, mass of the Mars, over r. Now, if we plug in me for that, we're going to get the square root of big G me over 9r. And I think we can see that that's going to give us square root of big G me over 9r. And that comes out to be the square root of 1/9 times the square root of big G me over r. So that's equal to 1/3 the original velocity. Okay, and now we can say and take the thing that says our original time was equal to 2 pi r over v0. Well, our new time, okay, so our new time, time 1, I guess, is equal to 2 pi r over 1/3 v0, or 3 times t0. Now, actually, I'm realizing up here I made a mistake, because here we said that the velocity is this. What I should have done there, and I'll do this in blue so I can highlight that it was a mistake, is to calculate the new time. It's not going to be this. I should have said, just like I did down there, t0 is equal to 2 pi r over v0. Okay, now t1 is going to be equal to 2 pi times 2r over, and it's square root of 2 over 2 times v0. So then that's going to go up there, and that's going to be 8 over square root of 2. That's going to be 4. So that's going to go up there and become 8. It's 8 over root 2. And 8 over root 2 can't have that. So that becomes 8 root 2 over 2, which becomes 4 root 2. So I get 4 root 2 pi r over v0. So I guess, actually, you know what I should have done is I should have just left, the 2 with this. Let me see. I should have left the 2 with this, so that would stay the original, and then say this is going to be 2 root 2 times that. So the original, whatever, the new time, the time of orbit compared to the original time is going to be the original time times 2 square root of 2. All right, and for those people who have lost, this was the new velocity, so I needed to plug it into the time function, and then by plugging in the time function, I can find the multiplier for time. Same way I did at the end of part C.